Okay, so here this part is about the power in the AC circuit. Okay, so here's the instantaneous rates of power dissipate in the resistor can be written as. Actually, this is for the RLC circuit. Actually, for this circuit. Okay, but the only element that consume power, the display power, is only the resistor. The capacitor and the inductor just alternatively store some power in the E field and B field. Okay, so they don't dissipate any power. The only element that dissipate power is the resistor. So actually, the power dissipation in this RLC circuit connect to an alternating EMF is only this part. Okay, PE equals I square R. So only relate to the resistor. Okay, so this is actually something like this. Okay, so this is the instantaneous. Okay, 中文叫做瞬时的。Okay, instantaneous rate. Okay, of power dissipation, which means that it is a sinusoidal function. So for every single moment, the power dissipate is different. So actually, we just take the square. Okay, so the square of the instantaneous current, and then multiply by the resistor. Okay, so this is a sinusoidal. This is a sinusoidal. Actually, this is sine square. Okay, if you still remember the trigonometry formula, okay, so this is like 1/2 minus cosine of 2 times this angle. Okay, so this goes to here. Okay, so this 1/2 is actually here, and then we will have another 1/2 of cosine. Okay, so it goes like this. So actually, we don't like this idea of instantaneous rate because it is time varying. Okay, sometimes it is 0, sometimes it is maximized. So here we would like an idea of average power dissipation. So take the average of this power dissipation. So for taking the power average, the conclusion is that it is half of the amplitude. Yeah, because it is quite straightforward if you just look at it. The average value will be like, okay, this half and this half will be like the same. Okay, so this is just in the middle. Or if you just do it rigorously using the integration, it can be like actually the P average will be like instantaneous of P dt from 0 to capital T. T will be a pure rate. Okay, so here this T will be like 2 pi over omega d. Okay, so take the average of a pure rate. Okay, so in this case, okay, so I square R will be like a constant moving outside. So what we need to care about is this sign of square. So for this sign of square, okay, so actually we still need to divide by T, yeah, because we just accumulate the power for time T. Okay, so we need to take the divide by capital T so that it's average out by the time. Okay, so if we just consider the sign part, okay, it will be like this, and then we have sine square will be this whole thing divided by 2. Okay, so these 2 go out. Okay, so actually this is the sine square will be like half of 1 minus this cosine of 2 times of this angle. Okay, so to integrate this thing, okay, for this one turn to a t, and then evaluate from t 0 to t will be 1t. Okay, 1t divided by 2t will be 1/2. Okay, so for the first thing, goes to here, 1/2. And then for the second thing, okay, it will be like integration of cosine will be sine. Okay, so negative sine of this stuff. And then evaluate from 0 to t will be like sine of 0 minus sine of 360 degree. So it is like 0 minus 0. So which is nothing but a 0. Yeah, because if you just take the average of a sine wave, the positive part and the negative part just cancel each other for a period. So this turns out to be a 0. So finally, this thing, okay, will have an average value of 1/2. So that's why this P average will be like half of absolute value of I square R. And then what we want to do is we try to separate these two into two parts, okay? 2 square root of 2 multiply together, and then we deliver to this absolute value of I. So it turns out to be like absolute value of I over square root of 2, and then whole thing square out. Okay, why we need to do this? Because for the instantaneous rate, it is I square out. But if we have I square R over 2 for the average power, okay, we don't like this factor of 1/2. So here we try to define another variable called the root mean square value. It's like an average value. But here what it really means is that we try to define this thing as the IRMS. Okay, so the IRMS is nothing but the I over square root of 2. Okay. So absolute value of I will be the amplitude, but for the RMS value will be this I divided by square root of 2. And then if you want to calculate the power, okay, it is related to the IRMS. So here, if we define this IRMS to be like this, then P average will be like IRMS square out. Okay, so it is like the form I square out. Okay, but we use another I. Okay, you will use IRMS rather than the amplitude of the sine wave. Okay, so in this case, we can define RMS to be I over square root of 2, and then also VRMS to be V over square root of 2. So for that case, okay, P average can be written as I square IRMS square R. Okay, so with this definition, but we need to pay attention. P average is not equal to IRMS times VRMS. Okay, so this is not correct. Although P of t is equal to I of t times V of t. This is okay, but this is not correct. Yeah, because this is the average power, this is the average current, this is the average voltage. Yeah, but they are not. This equation does not hold. The reason is that the current and the voltage are not in phase. Yeah, if we have a phase here, so they are a little bit off. Yeah, because the idea is like if we try to have, let's say, P average will be like integration of P of t dt, and then from 0 to t. And then actually this is still correct if we make it like let me see, V of t times, it is still correct if we make it like V of t times I of t. So V of t will be like V cosine of omega dt. okay, something like this. And then we also have this I, and then cosine of omega dt minus phi dt. So V and I just go out, and then the remaining stuff will be like cosine of this thing times cosine of this thing, and then we do the integration. So yeah, so I'm not sure whether you still remember this. Okay, so you try to multiply two cosine together. So you can just make it like the angle added together and the angle subtract to each other. So if the angle subtracts, okay, it remains the cosine of phi, okay, and then the remaining thing will be like cosine 2 omega dt, okay, cosine 2 omega dt. So it will goes out at another 1/2, okay. So it turns out to be like IRMS, VRMS, okay, when the two deliver to one half to this V, 1/2 to the I. So it turns out to be IRMS, VRMS, and then with the cosine. And then the other stuff, and then when you add them together, it turns out to be a 0, yeah, because it is still a sinusoidal with a double frequency. So when you integrate it, it turns out to be 0. So if you have interest, you can just calculate forward, okay, move forward for this thing, and then you will find out, okay, why we get this cosine phi here. So this is not correct, so this one will be correct because the I and V are not in phase. Okay, and then here we will say this is the power factor. This is the power factor of the RLC. Okay, of the RLC. Okay, so here with a sample problem. So here it says a series RLC circuit driven with ERMS 120 volt at the frequency FD to be 60 Hz, and then contains a resistance R, and then inductance with a ZL, and then also capacitance with a ZZ. Okay, what are the power factor? Okay, what are the power factor cosine phi, and then the phase constant phi, okay, for the circuit. Okay, so here we have a Z equals R plus J, or I could say it should be R, or maybe R plus ZL plus ZZ, okay? So it will be R to be 200, and then plus ZL is J80, and then this is J negative 150. So J80 minus 150. Okay, we just add them together. So it turns out to be 200 minus J70. Okay, the SI unit is still ohm. Okay, so here we have phi to be arctangent of the I mean the imaginary part is negative 70 over 200. So this is negative 19.3 degree. Okay, so the real part is positive. Okay, the real part is positive. The imaginary part is negative. So this is in the fourth quadrant. So phi is a negative 19.3 degree. Okay, and then finally, cosine phi will be cosine of negative 19.3 degree, which is 0.944. Okay, so this is the power factor. So cosine of something won't have any units. Okay, won't have any units. Okay, so this is the power factor. And then for question B, what is the average power P average dissipate in the resistor? So actually, just we call that Z is 200 minus J70 ohm. Okay, So if we take the absolute value of z, which will be 200 square plus 70 square, or negative 70 square, so that will be 211.9 ohm. Okay, so this is the absolute value of the impedance. Okay, so P average will be ERMS square over absolute value of z, and then cosine of phi. So why is it like that? The reason is that this is nothing but VRMS, IRMS, and then cosine of phi. Okay, so VRMS is nothing but ERMS. Okay, so this is ERMS. And then for this, IRMS will be ERMS divided by absolute value of z. Okay, so it will be like ERMS squared divided by the absolute value of z. So this will be 120 squared over 211.9, and then times cosine of phi will be 0.944. Okay, just as what we calculated in the previous page. So finally, this is 64.1 watts. 64.1 watts. Okay, so this is not that, so you just need to make use of the equation. Okay, so for the part C, so it asks what new capacitance C new is needed to maximize P average if the other parameters of the circuits are not changed. Okay, so the idea here is we try to make the imaginary part to be 0. Okay, we try to make the imaginary part to be 0. So for other part can be changed, we try to make the imaginary part to be 0, which means that the ZC new will be negative of ZL, so that they add up to be 0, so that the total impedance will be a pure real value. So here, what we try to do is ZC new will be negative ZL, so it is nothing but negative J80 .0 ohm. Okay, so this is the new capacitance. Okay, new capacitance. Actually, the new the new impedance. Okay, so this is not the capacitance, but actually we have we know that, okay, this is actually 1 over J omega C nu. Okay, so we can calculate that C nu will be J square will be -1, and then with also this negative side be positive, so it turns out to be 80 times 2 pi 60, something like this. Okay, it turns out to be 33.2 microfarad. Okay, 3.2 microfarad. So if you change the capacitance to this value, so the imaginary part, for the impedance of the inductor and the capacitor will perfectly cancel, so that in that case, of course it is not asked by the question, but I will say that, okay, this Z will be nothing but ZR, which is 200 ohm. Okay, and then finally the amplitude of the oscillation will be maximized. Okay, so So here is the transformers, okay, is the transformers. So for the transformers, okay, I always say that, okay, so in the real world there are 3 types of transformers, okay. So one is the Optimus Prime, okay, 变形金刚. And then the second type is this one, 变压器. And then, yeah, when I first tried to taught this course, okay, at that time I just say, okay, there are 2 types of transformer, okay, the 2 I just mentioned. But here, another well-known type of transformer is the one in the AI, okay. Actually, I don't think there is a popular Chinese name for the transformer in the AI. Okay, we always just call it is English name. Okay, so if we really need to give it a Chinese name for that transformer in the AI, it turns out to be something like 转换器或者是翻译器. Okay, it will be like very low. So I think, yeah, the AI guy don't try to call it Chinese, okay, or try to make a Chinese name for it. Just try to call it Transformers, okay. So maybe you don't really know Transformers, okay, but actually recent year we have ChatGPT, okay, ChatGPT. So actually for the ChatGPT, of course chat is chat, okay, so GPT, what does it mean? Okay, GPT means generative pre-trained transformer. Okay, of course it is out of the scope of this course, but just let you know, okay, so this is the third type of the transformer in the world. So yeah, so 是一个生成式的预训练的 transformer 的模型，这叫做 ChatGPT. So it is like you try to generate something. Okay, so if we try to generate some text, it is like, okay, so try to adding words by words. Okay, 就是在做那个文字接龙。OK， 就是他觉得前面一个问题或者前面一段话，他就一个一个字接上去，看哪一个字合适，他就一直写，就是好像你写作文的时候，你就没有去想，你就写到哪里就加一个字上去，就那种感觉。Okay, so it's like transformer. So going back to here, so we talk about the second transformer. So the 变压器 here. Okay, so here a transformer assumed to be ideal is an iron core on which are wound. Okay, primary coil of NP turns. Okay, so we have a primary coil NP turns and a secondary coil NS turn. If the primary coil is connected across an alternating current generator, the primary and secondary voltage are related by Vs equals Vp times Ns over Np. Okay, so the graph is somehow like this. Okay, so here we have the primary coil. We have also the secondary coil. Okay, so for the primary coil, we try to connect an alternating EMF. Okay, so an alternating EMF is like a EM times cosine of something. So which means that if you take the derivative, cosine turn to sine, and then turn to cosine turn to negative sine, and then negative cosine, and then going back negative sine or positive signs. Okay, so back and forth. So you can infinitely take derivative for a sinusoidal, and then it is still a sinusoidal, making it like cosine sine cosine sine. Okay, back and forth. So it never turns to a zero. Okay, if you try to take derivative for a sinusoidal. So the idea I mentioned, the derivative is that in chapter 30, okay, we learned the Faraday's law. So which means that if we try to provide a sinusoidal current for the first coil. Okay, according to chapter 29, it will have B equals mu 0 I 2 pi, sorry, it should be like mu 0 I n, okay, mu 0 I n. Okay, mu 0 I n. Okay, so in that case, this I is sinusoidal, so which means that this B field is also sinusoidal. It's also sinusoidal. So which means that, okay, we try to add a magnetic ring here so that it can deliver all the B field line to the secondary coil. So the idea here is like this. So in that case, it try to generate some B field, and with NP turns, so it will be like phi B will be like yeah, so it will be like time or also multiplied by NP, so proportional to this NP. And then finally, for the Faraday's law, it will be like NS times negative d phi b dt. So this phi b is proportional to this b, and then okay, also it will be also the derivative of it, and then also proportional to this ns. So finally, this Vs, the secondary voltage, will be of course proportional to the primary voltage, okay, the primary voltage, and then it will also proportional to Ns, yeah, according to the Faraday's law, and then this Np will be like yeah, so this is inverse proportional to this Np, so something like this, okay, something like this. So at the very first, we have this one, okay, which is like, or you can also write it as Vs over Vp is Ns over Np, which means that the voltage, okay, the voltage of a coil is proportional to the number of turns, okay, to the number of turns. And then here, okay, it also have this energy transfer, and then we assume this transformer to be ideal, which means that no energy is lost, no energy is leakage. So of course there will be some B field, okay, just leak out, but we just assume all the B field delivered to the secondary coil, and then all the power are also transferred, or all the energy are also transferred to the secondary coil, so that we try to assume that we have a conservation of energy. So for the primary coil, yeah, we don't assume there are some C and L, okay, so that I and P are in phase, okay, we just assume I and P are in phase. So I and P, IPVP will be the power, okay, the power for the primary coil, and then IS times VS will be the power of the secondary coil, and then we assume there are no energy loss, so that we assume IPVP will be equals to ISVS. So here we have actually IP over IS is actually VS over VP. So which means that, yeah, because they have the same power, so which means that, and then V times I will be the power. So which means that if V is large, I will be small. If I is large, V will be small. So which means that for the current, okay, the current is inversely proportional to the voltage, and then the voltage is proportional to the number of turns, which means that if you plug in this one to here, so this one we have IS over IP will be NP over NS, which means that the current will be inversely proportional to the number of turns. Okay, if more turns, the current will be smaller. Okay, so in that case, there will be an interesting property, which is like R equivalence. R equivalent means for the first turn, okay, for the primary turn, we have, actually for the secondary turn, okay, we assume that after we deliver the power, this power will be consuming by a load, okay, consuming by a load. Okay, we don't know what is this load. Maybe it will be a line, maybe it is an equipment or anything resistive. Okay, so this power will be consumed by the load with a resistance R. So which means that for the secondary coil, Vs over Is must be R. Okay, it should satisfy the Ohm's law. However, for the primary coil, as long as we have this Vs over Vp to be proportional to the number of turns, and then we also have this Is over Ip to be the inversely proportional to the number of turns. So that if we try to make, we try to make 1 and then 2 here. So if we just divide 1 by 2, so Vs over Is, okay, Vs over Is will be R, and then in the denominator we have Vp over Ip, which is so-called the R equivalent. So here we have a R equivalent to be Vp over Ip, the equivalent resistance for the primary coil. Okay, so here we have a Ns over Np and then whole square. Okay, so after dividing this stuff, and then we try to move Req to the other side, and then we also move this to the left side. So it turns out to be Np over Ns whole square multiplied by R will be R equivalent, which means that on the secondary coil we have a resistance of R, but for the first coil, or for the primary coil, the resistance is seen is multiplied by the ratio of the number of turns square. Okay, this thing we will call it the impedance transformation. OK， 就是有一个叫做阻抗的转换，就是你在第二圈的时候，你看到一个电阻，比如说比较比如说第二圈比较怎么说呢？这个比较多圈，这个比较少圈。然后比如说你看到一个 R 是这个电阻比较大的，那你在第一圈的时候，这里的 impedance 就会比较小啊，就会受到这个 turn ratio 的改变啊，因为这个比如说 Np 小，这个 Ns 大，那 Np 除以 Ns 就是小于1嘛，那平方的话就会更小。OK， 就会转换这个阻抗，就是第二圈跟第一圈看到的。阻抗对不一样，这会不一样。So actually we can make use of this property, okay? We can actually make use of this property. So let's take a look at this sample problem. So here is a transformer on a utility pole, okay? Utility pole operate at Vp equals 8.5 kilovolts on the primary side. And supply electrical energy to a number of nearby houses. OK， 就是一些变电站。OK， so we have Vs to be 120 volts. OK， Vs 120 volts. Both quantity being RMS value. OK， RMS values. So assume an ideal step-down transformer, a purely resistive load, and a power factor of unity. Okay, so of course this is quite ideal. Okay, just as an example. So, what is the turn ratio Np over Ns of the transformer? Okay, so NP over NS is nothing but VP over VS. Okay, so it is proportional to the voltage. So this is 8.5 times 10 to the third power over 120 volts. Okay, so 120 or in miniature 110, okay, would be the RMS value. So if you consider the amplitude, you need to multiply by square of 2. Or in Macau is 220 volt is also RMS value. So if you multiply by square of 2, it's around 310. I'm not really sure the number. So just check out by calculator. But yes, the idea is like that. So this is 70.8. Okay, the ratio, the turn ratio is 70.8. So this is trivial. And then for the question B, so the average rate of energy consumption in the houses served by the transformer is 78 kilowatts. 78 kilowatts. What are the RMS current in the primary and secondary of the transformer? Okay, so for the IS, okay, it's the secondary coil, P average over VS, okay? So because we just assume the power factor of unity, power factor of unity, so cosine of phi will be 1. So here we have a 78 times 10 to the third power over 120 will be 658. Okay, so this is the current for the secondary transformer. But for the primary transformer, IP will be P average over VP. Okay, so this is 78 times 10 to the third power over 8.5 times 10 to the third power. So this is 9.28. Okay, so if you are familiar, so this is just a ratio of 70.8. Okay, so if you divide 650 by 70.8, it is actually 9.28. Okay, so these are the current for the primary and secondary coil. So for question C, what is the resistive load RS in the secondary circuit? What is the corresponding resistive load RP in the primary circuit? So RS will be VS over IS, which is 120 over 650, so which is 0.18 ohm. Okay, so we already know all the values. And then for RP, which is VP over IP. Okay, so 8.5 times 10 to the third power over 9.2. So this is 926 ohm. Okay, so this is a high impedance for the primary coil, and then low impedance for the secondary coil. Okay, so actually the sample problem is up to here, but I will tell you the story about why we need the high voltage to transfer the energy. Okay, so actually even in the power factory, the voltage is even higher. It's around 300 kilovolts, something like that. Okay, depends on different country. Okay, can be like 几十万伏的，就是如果是电厂出来的电的话，那然后它就会输出来的时候，它会先降一级，降到几千，然后到变电站的时候再降一级。So this is the case. Okay, so it's already go to the utility pro already. Down convert to like 8.5 kilovolt. So the idea here is, so here we have the VRMS to be 8.5 kilovolt, and then we have this out. Okay, we have this out to be to be small, okay? And then this will be the transformer model, okay? This will be the transformer model. And then finally it goes to RS to be 0.18 ohm. And then here we have NP to the NS. Okay, so actually, if finally we have the loading to be 0.18 ohm, and then with this turn ratio, okay, with this turn ratio, so in that case, we will see this impedance is much larger, okay? Yeah, as much as we have the turn ratio to be 70.8, okay? So this will be 70.8 square multiplied by this 0.18 will be 900 something. So, of course, the power transferred from the factory will be like far away from our home. So this is a very long wire. So if we accumulate a little bit of resistance, okay, if it is still much smaller than the 926 ohm, then the power dissipated by the wire will still be low. But if we don't use this transformer, okay, we don't use high voltage to transfer the power, it will be like if we have this RS and then we directly connect it to the source, and then we provide you a 125 volt far away from your home. So it will be like this is 0.18 ohm, and then this is really long, okay? This is really long, can be like kilometers long, okay? Or even tens of kilometers. So in that case, okay, so this, if this out is comparable to this 0.18 ohm, then there will be quite a lot of energy consumed by the wire, okay? So that's why we need to transfer the power with high voltage, okay? Transfer with a high voltage, so that for this case, okay, it has high impedance, which means that the voltage is high and then the current is low. So the power dissipation for the wire will be like I square R. So if we have a low I, then the power consumption by the wire will be low. But here, if we don't use the transformer, if we don't use high voltage transfer to transfer the power, so we have a large I. So I square times R will be large. So there will be quite a lot of energy loss in between. Okay, so that's the story about the power transfer.